Well, welcome, everybody. I'm John Holdren, President Obama's Science and Technology Advisor, and it's a great pleasure to be here to welcome you to this happy, important, celebratory event where we're pleased to honor two real giants in American science and engineering, Mildred Dresselhaus and Burton Richter. Our awardees have already had a pretty good day today. A few hours ago, Secretary Chu and I joined them in the Oval Office where President Obama offered his congratulations. And as is always the case when he meets leading scientists and engineers, he displayed his genuine enthusiasm for science, engineering, technology, innovation, and STEM education in science, technology, engineering, and math. And he thanked Millie and Bert not only for their important technical contributions, but for the role that both of them have played in wide-ranging engagement in the science and society issues that are so important to get right in today's world. Let me also remind you that this is the same president who on Friday, in an event more typical of other presidents, met with the NCAA champions, the University of Kentucky's men's basketball team. And it was great to see that today he kept his repeatedly expressed promise that if sports heroes are going to have their day in the White House, then the White House is also going to celebrate winners in science, engineering, and math, and the top-ranking educators that teach in those fields. And in fact, the president has occasionally said to me after meeting with leaders in science and math and engineering and STEM education, he said, I wish I could meet with more scientists and fewer sports teams. So it's great that the president understands that while people like Drs. Richter and Dresselhaus are perhaps not on the covers of magazines, well, at least not on Sports Illustrated, maybe Physics Today, and they're not being chased by paparazzi, at least most of the time, they're still real all-stars and heroes whose work has benefited the nation and benefited the world. I think Dr. Brinkman in a minute is going to be speaking a bit about the Fermi Prize itself, so I'm not going to go into detail about that award other than to say the obvious, that it's no small matter to receive from the White House and the Department of Energy a solid gold medal embossed with the image of one of the most impressive and accomplished scientists in history, a great theoretician, experimentalist, inventor, architect of the first nuclear reactor, Nobel laureate, whose name today graces a research institution, an accelerator lab, a gamma-ray space telescope, a nuclear generating station, a class of particles, and a synthetic element, as well as gracing the Enrico Fermi Award that's being bestowed today. In any case, Millie and Bert, you are joining and adding further luster to an extraordinary list of previous winners of the Fermi Award, and I couldn't be more delighted at being able to be here to share the occasion with you. So I want to personally congratulate you both again. Thank you for your extraordinary contributions, both as explorers extending what is known about our world and how that knowledge can be put to productive use, and also as educators and real sources of inspiration, because I know both of you have long been committed to the essential task of preparing the next generation of science and technology leaders. In closing, I'd like to read a portion of the letter that President Obama has provided to each of our awardees in honor of their achievement. In that letter, the President reminds us that it's incumbent on all of us to take the latest discoveries in physics and engineering and apply them to pressing national and global needs in the energy domain, the domain in which not only our awardees, but Secretary Chu and Dr. Brinkman here at the front of the room are working so hard on every day. That letter reads in part, quote, "Today it is essential that Americans carefully consider our energy use and imagine new approaches to growth that are not only economically sound, but also environmentally sustainable. Your groundbreaking work is imperative to moving energy-related science forward and helping nations around the world confront critical challenges. By collaborating with scientists in related disciplines and engaging with policymakers and supporting our next generation of doers and makers, you are improving the world around you and sowing the seeds for future innovations. Congratulations again, and I wish you all the best." And it's signed Barack Obama. So congratulations indeed. Let me now turn the microphone over to Dr. Bill Brinkman, Director of the Energy Department's Office of Science, and one of the leaders in the crew of distinguished scientists and engineers working in this administration. Bill.
Thank you. Thank you for your welcome, Dr. Holdren. It's our pleasure to have you with us, as it is for all of those who have come from the White House offices, government labs, and departments and agencies. I'm also happy to see Ralph Cicerone here. Back there he is, who is president of the National Academy of Sciences. I welcome people from the Department of Energy. There's Deputy Secretary Poneman. Is he here, or did he not show up? He didn't show up. But acting Under Secretary of Energy, Arun Majumdar. Under Secretary of Nuclear Security and Administrator for the National Nuclear Security Administration, Tom D'Agostino, and the Deputy to Tom D'Agostino, Neil Miller. Now, all three here today. It's nice to have you. In addition, we have lab directors who have come from various parts of the country to be here today. Eric Isaac, there. Paul here? No. Tom Mason from Oak Ridge, and Persis Drell from SLAC. Of course, she has to be here because is one of her people. And so it's a very important thing, and it's very, very nice to have. Okay, finally, I'd like to express my gratitude to all those who joined us from Capitol Hill, and we appreciate them coming. We are gathered here to present the Enrico Fermi Award, a presidential award that honors scientists of international stature for a lifetime of exceptional achievement in the development, use, or production of energy, fields that Enrico Fermi pioneered. He has rightly been called the last of the double-threat physicists, for he was a genius at creating both fundamental theories and elegant experiments. During his lifetime, Fermi was made many theoretical contributions to every major discipline of physics, whether it was solid-state physics, astrophysics, and particle physics. He also was a superb experimentalist. There are many things which has a name attached: Fermi-Dirac statistics, Thomas Fermi approximation, et cetera, et cetera. He truly was an outstanding multi-variable physicist who did a lot of different things in his life. The award named after him is the oldest science and technology award given by the U.S. government. As one of the most prestigious science honors in the world, it is given for three purposes: to encourage excellence in energy science and technology, to show appreciation to the scientists, engineers, and science policymakers who have dedicated their lives to the benefit of humankind through energy science and technology. I think there are no two people I know of who exemplify that more than these two honorees today. Finally, to inspire people of all ages through the example of Enrico Fermi and by the examples of our Fermi Award winners, laureates who followed in his footsteps. And once again, I think if you listen to Millie Dresselhaus's story, you will realize what an important role model she was for so many people for so many years, particularly women. Over the past 56 years, there have been 62 Fermi Award recipients. From the earliest, John von Neumann, E.O. Lawrence, Eugene Wigner, and Glenn Seaborg, through the most recent Fermi laureates, all have benefited humankind through careers marked by exceptional contributions to fundamental science, energy, and technology. And this is certainly true of our newest recipients. Doctors Dresselhaus and Richter have distinguished themselves greatly in science and service. Through their exceptional work, they have proven worthy followers of Enrico Fermi and outstanding examples in their own right. So now, to present the Fermi Awards, it is my honor to introduce Secretary of Energy Stephen Chu, a distinguished scientist and co-winner of the Nobel Prize in Physics in 1997. We are pleased and proud to have a scientist leading the Department of Energy. As President Obama said, the future of our economy and national security is inextricably linked to one challenge: energy. Secretary Chu has shown exceptional leadership of the Department of Energy over the past 3+ years. Under his leadership, we've brought significant new resources and innovative new approaches to the department's research and development mission. We are breaking down stovepipes between existing basic and applied science teams and have launched new research models like the Energy Frontier Research Centers, the Energy Innovation Hubs, and ARPA-E. The early results are something that we are all excited about. These modalities, along with activities such as ARPA-E Summit, have placed the conversation on energy and climate on the national agenda. Our investments in wind and solar power have put the country on track to double renewable energy generation from 2008 to 2012. We've partnered with utilities, local communities, and other federal agencies to accelerate America's transition to a stronger, smarter, more robust power grid, including more than 30 smart grid and energy storage demonstration projects nationwide. The Secretary reconstituted the Secretary of Energy Advisory Board. Several subcommittees have been formed, including a distinguished panel of experts that delivered a blueprint for how America can safely harness the vast shale gas resources while protecting our land and waters. We released a strategic plan to guide our mission of ensuring America's security and prosperity by addressing its energy, environmental, and nuclear challenges through transformative science and technology solutions. Secretary Chu willingly gave up much of his career as an outstanding research scientist to help our country and the world address these issues. Please welcome Secretary of Energy Stephen Chu.
So Bill actually went through a lot of what the Fermi Award was about, so I'm going to skip down and tell you a little bit about Enrico Fermi, because in awards like this is the custom, and each time I do it, I just add more to it. And so, you know, maybe 10 years from now, it's going to be an hour lecture. And then I'm going to talk a little bit about both Millie and Bert. Okay, so first, Enrico Fermi. The guy was bright, very, very bright. No surprise. But how bright? Well, you can't really tell. He got a PhD. No, don't worry. He got a PhD when he was 21. But by the age of 25, he had formulated the quantum statistical law of Fermi statistics. Okay? The Pauli exclusion principle, the quantum mechanical laws of Fermi statistics, and fermions, which, for those of you who are not physicists, the Pauli exclusion principle says that a quantum particle and another quantum particle can't occupy the same quantum state. So you might ask, how is it that two fermions can share the Fermi Award? Well, it turns out they have many, many degrees of freedom, and so they can actually sit in the same chair in the exact same space, but all those other degrees of freedom, it's okay. You can share the award. All right. Now, he was awarded the Nobel Prize in 1937, and I'll read the quote. It's for his demonstrations of the existence of new radioactive elements placed by neutron radiation. This is the presentation, and for his related discovery of nuclear reactions brought about by slow neutrons. That's his citation. And so here we go. We're going to have the first picture of his group. Oops, wait a minute. There we go. This is, good. This is his group that he assembled around him called Via Panasperna Boys. I don't know if I'm really doing terrible to the Italian. But you look, first of all, at Enrico Fermi. He was 33. And all these guys were pretty young. And he had put together this team to look at what you can do about neutrons. And this team was known for working night and day, absolutely crazily hours. This is the address where their laboratory was. So in the Nobel Prize, there's a presentation to the king that's explained by someone in the Nobel Committee. And so I'm going to say what he said. with what we know today of the structure of atoms, we understand perfectly the hopeless task undertaken by alchemists of old. So what did Fermi do? He actually took atoms, irradiated them with neutrons, and turned them into other atoms. So it was alchemy. All right? Now, his Nobel contributions don't start all from scratch, and there were a few precursor alchemists that also were turning atoms into something else. The first important one was Lord Rutherford. And Lord Rutherford did the first alchemy experiment. He's the Rutherford of Rutherford scattering, using an alpha source and bouncing them off the nuclei. But he also found that the alpha particles would actually go into a nucleus sometimes, some intense regurgitation, and out would spit, let's say, a proton, and the nucleus would change in atomic number, hence element. Okay? So nitrogen, for example, turns into oxygen by absorbing an alpha and spitting out a proton. So he was awarded, there's going to be a lot of Nobel Prizes in this because it's to tell the non-scientists how important this work is. He was awarded a Nobel Prize in 1908 for this work. The next important step, and I was following Fermi's Nobel lecture, and then the next important work was made by Irene and Frédéric Joliot. And let's see, it's a husband and wife team. They got it in chemistry, and there they are. And what they did is they took these alpha particles and they found that not only can you make something like nitrogen and oxygen 17, which was stable, you could also make unstable, short-lived radioactive nuclei. And by bombarding alpha particles with various elements, they found that you can actually make artificial radioactivity, which by that time was considered very important because radium, which was being used in hospitals, was very rare and a very costly process, and now all of a sudden you can make artificial nuclei that would decay. So it was a big deal. Now, just in case you're wondering, does that Irene Curie have anything to do with the other Curie? And the answer is yes. She was the daughter of, and this is an earlier picture of Irene and Marie Curie in a Belgian hospital, actually applying the radium to medicine. So now, and you're going to bear with me because I'm going to do a lot about these women because it's very important for some of the themes here, so just stick with me. And so Marie Curie, with her husband Pierre Curie, shared a Nobel Prize in 1903 with Henry Becquerel for research in radiation. And I'm going to show you another picture. There's his. This is Pierre and Marie at their wedding day. It was a wedding photo. Very handsome, very charming couple. And so now, so that continues. Now I've got, oops, I got to read the quotes from my notes. And they had two beautiful children. And this is the older daughter, Irene, at age 8, and the younger daughter, Eve, at age 1. So after Irene was born, there was a bit of a crisis because, Marie wanted to raise her children, her child, first child, and her second child, and she felt very responsible, but she also was very much a workaholic, and she actually discusses this dilemma. And she writes in her autobiographical notes, "It became a very serious problem how to take care of our little Irene and of our home without giving up my scientific work. Such a renunciation would have been very painful to me, and my husband would not even think of it. He used to say that he had got a wife made expressly for him to share all his preoccupations. None of us would contemplate abandoning what was so precious to both." So they pushed on, and she still figured out how to do this. And, if you read later on, she said, yeah, especially if the child got sick, there's just a couple of sleepless nights, but, you soldier on through. Now, so you just learned Irene got a Nobel Prize, the second woman to get a Nobel Prize. Marie was the first. Irene's father got a Nobel Prize. What about poor Eve? Okay. So poor Eve was not a scientist, but she was a touring concert pianist early in her life in France and Belgium. And then she became an author, a journalist author, and she actually wrote a book called Madame Curie, later turned into a movie starring Greer Garson, Walter Pidgeon. She also wrote another book, Journey Among Warriors, which tells of her journeys among some of the people during her life. Both were bestsellers. Now, Eve was totally devoted to her mother, and her mother then got ill and began to die of leukemia, and Eve actually nursed her during her final days and was very supportive during the earlier times. So, and then her mother died at the age of 66, 1934. Sadly, Irene succumbed to the same disease, leukemia, in 58, and it was, quite frankly, it's because of their work on radium and other radiation. So, what happened to Eve? Well, she remained single for 20 more years, became during this time a vocal supporter of the French underground, the Free French. After the Nazis occupied France, she became a special advisor to the Secretary of NATO, and then on a few weeks before her 50th birthday, she married a man, Henry Laboussier. Now, Henry turned out to be working at the United Nations, and he had been the executive director of a new organization called the United Nations Children's Fund, otherwise known as UNICEF. And in 1965, he got a Nobel Prize for peace. So there she is, poor Eve, saying, there are 5 Nobel Prizes in my family, 2 for my mother, 1 for my father, and 1 for my sister and brother-in-law, and 1 for my husband. Only I was unsuccessful, okay? It's a tough life. But she was an accomplished musician and author, and oh, by the way, she wasn't bad looking. She was actually famous in France during the 1920s and 30s. So because she married at age 50, I think she had other possibilities. And these are actually fashion photos taken of her in her 20s and 30s. So anyway, this is a weird family, but it gets weirder. And so please bear with me. So now Marie is about to accept her Nobel. So, I have to say that Pierre died very tragically in 1906. He was in a meeting. He had to go across Paris. He's running across. He goes to the meeting. There's a few issues he wants to talk about, appointments and laboratory safety. He wants to improve the laboratory safety. And then he comes out and he's rushing, and he doesn't really pay attention, as his assistants would say, where he's going. And he sadly gets run over by a heavy wagon, okay, and he dies. And Marie just goes to pieces. She's just in deep depression. And so she, for many years, just refused to even talk about him. She just plowed herself back into work. But then, and that was 1906, and by 1911, she was going to accept her second Nobel Prize, this time in chemistry. And then, just before that, rumors started swirling that Marie was having a love affair with another brilliant physicist, Paul Langevin, of Langevin equation. Okay? And this was years after Pierre died, so that wasn't the issue. Langevin's marriage was failing, that wasn't the issue. The fact of the matter was Langevin was still married. And now, and also very innocently, so don't read anything more into this, Langevin happened to be a colleague of Marie's, but also was a student of Pierre's. But that wasn't that. But tongues were wagging. Okay, so the French were going to try to solve through this, but not really, because Marie was getting pretty successful, and there was beginning to be resentment, actually, in the scientific circles, surprisingly, you know. And then Arrhenius, the great a Swedish physicist who was very powerful in the Nobel Academy. First wanted her to come and accept it, but as the tongues began to wag a little more, he said, well, maybe you shouldn't come here until your name is cleared, to which Marie wrote back, the prize has been awarded for the discovery of radium and polonium. I believe there's no connection between my scientific work and the facts of private life. I can't accept that the appreciation of the value of scientific work should be influenced by libel and slander concerning private life. I'm coming. She didn't say I'm coming. That's me adding that. So she came. And a year later, the scandal died down. But that's Marie. And Langevin legally separated from his wife. They never connected up together. They were friends. And it turned out their grandchildren, Helena from Marie's side, and Michael from Langevin's side, married. So there's a little family connection here going on. Okay, so, but I'm digressing. I want to go back to Fermi. So, all right, now I just talked you through Lord Kelvin, Irene Curie, and that led to this radioactivity. But what Fermi did with his team was that they found, instead of hitting things with alpha particles, you can hit them with neutrons, and they found out with thermalized neutrons. And then they found out just about everything becomes radioactive if you hit it with a neutron. And so this was alchemy on a big scale. And so he got the Nobel Prize for that. Now, it's 1938. He never went back to Italy because Mussolini was in power, fascism was taking over, and he decided he could not stay there. So immediately after the prize, I don't even think he went back, or at least it was unclear to me, at least at 4 a.m. in the morning. So he went to the U.S., starting at Columbia University. Now, so at Columbia University, he starts with doing all this neat stuff, and he then moves to Chicago. I will get a little bit behind to move to Chicago, but he discovered, while I was doing this work with the neutron activation, fission was discovered in 1939 by Hahn and Strassmann. And Fermi actually just narrowly missed it himself, which is really unfortunate because if he had discovered fission, he could have been famous. But because he was so on top of it, immediately he knew that there would be secondary neutrons, and if with secondary neutrons, could you get a chain reaction going almost instantaneously? And so he was going around talking about this. So he's at Columbia, he's doing some neutron work, and then he moved to Chicago in the early 40s. And why did he do that? Well, he did that because he was urged upon him by events beyond his life. In the spring of 1941, the National Academy of Sciences, I see Ralph sitting there, was charged, and a committee was formed and chaired by Arthur Compton, and they were asked to study the feasibility of nuclear weapons. This is the spring of 41. December of 41, Pearl Harbor. And then they decided to fast-track this research. And so in Chicago, they formed what is called the Metallurgical Lab, affectionately known as the Met Lab, and not to be confused by a meth lab. So the Met Lab was formed and established in February 1942. All right? So, wait a minute. There we go. Where am I? Page 6, page 5, page 7. Here we go. Okay. So, so they started this work, and Fermi was tasked to build the first sustained nuclear reactor. And it was built underneath Stagg Field, which was the football stadium at the University of Chicago, shown in the bottom right. Underneath there were some squash courts. They converted the squash courts and used the space into the thing on the left-hand side, which is affectionately called Chicago Pile 1. And Now, you know, everybody was sniffing around looking at it, and of course there were some Soviets sniffing around looking at that, and, you know, and Fermi told them that they were doing this in a squash court. It was mistranslated, and it came out that they were doing it in a pumpkin field. Anyway, during this time, Fermi was known not only for a theorist and experimentalist, but he really personally oversaw everything. He did many of the detailed calculations of the reactor himself. He was a brilliant project manager. He had enthusiasm, and he was really hands-on. How hands-on was a fellow, so the story goes, and I have a reference in this of where you can find these things. But in any case, this person's looking for the great Fermi, and he's saying, where is he? He's not in his lab, he's not in his office, where is he? They found him in the machine shop. He's shirtless, he's sweating, he's pushing graphite blocks through a bandsaw. He's sawing them himself because he had to get on with it. And he was really very, very hands-on. Now, it's actually have somewhere in my drawer somewhere, I have a little bit of the original graphite block of that Pile 1 reactor. It's about this big. So that's really totally cool. But, so, now, Lawrence, so this was, now we're in World War II. It's 1942, February 1942. December 1941, Pearl Harbor. They're moving this at a fast track. And Compton, a very distinct, again, a Nobel laureate, tasked, okay, get these scientific guys to do something. We got to move fast. And so now Compton moves the uranium, the reactor work to Chicago. Why? Because he was a faculty member in the University of Chicago, and they didn't have conflict of interest rules in those days. So, or something. Now there was a bit of a reaction against this, and Lawrence, E.O. Lawrence, was really quite upset. He said, quote, "You'll never get the chain reaction going there. The whole tempo at the University of Chicago is too slow." Compton took umbrage, and so he said, okay, I think they can get this done in 6 months. 6 months, from scratch. And I'll bet you a 5-cent cigar. And Lawrence took him up on it. They won, Compton won the bet with 1 month to spare. They got the sustained reaction in 5 months. That is project management. Okay, so, and then as soon as that success, Compton calls James Conant, who is the chair of the National Defense Research Committee, and gives us impromptu coded messages. It wasn't really rehearsed, and says, Compton says, "The Italian navigator has landed in the New World." Corinth. How are the natives? Compton. Very friendly. Anyway, so on goes Fermi. Fermi was a legendary lecturer and teacher. You know, we have Feynman giving his lectures in physics where he didn't write them down. He had scribes, and they were transcribed, and he would kind of maybe look them over, but he had 3 other professors doing this. Fermi, similarly, when he gave lectures, gave lectures on quantum mechanics, thermodynamics, and nuclear physics, also had a scribe. They also turned in little notes, and I started reading these when I was a graduate student at Berkeley, and actually, later on at Stanford, where I give lectures, especially the thermodynamics and quantum mechanics, I would always go back to these. They are jewels of elegance, simplicity, get right to the heart, no messing about. And this is Fermi's style. But now here you see Fermi. He's got, for those of you who don't know, the top line is the Hamiltonian operator. The time dependence is equal to p squared over 2m minus e squared over 2. Do you notice this little eraser sign? There was a plus, he erased and put in a minus. That's good, so he fixed it, or maybe one of his students said, okay, you got this wrong. The next line, alpha equals h bar squared e over c. It wasn't quite fixed. We think that's alpha, the fine structure constant, which is e squared over h bar c. And so the beautiful thing about this is this gives me so much comfort, because when I'm lecturing and give these boo-boos and some students say, nah, even Fermi can do this. So even Fermi can make mistakes, and as well as being a brilliant lecturer. And when I was doing this, my quantum mechanics little book was in the department, so I couldn't find out whether he really meant alpha to be that, but I think it's that. So anyway, he also was a great mentor, a fabulous mentor, not only to many, many PhD students, but many other people in University of Chicago. And for those, and we'll probably hear more about this from Millie, for those who were living at Chicago at the time, and I know veterans at that time, that he kind of defined the intellectual tone at Chicago in many respects. He, again, had many, many students. 5 of them, well, actually not that many students, but 5 of them went on to get Nobel Prizes, but he certainly influenced the whole tenor. So that's Enrico Fermi. So now let me shift to Millie and Bert. Do I have enough? How much more time do I have? Minus 20 minutes. Okay. So Millie started out in a college called Hunter College, and she writes of her decision to go to Hunter College. Quote, "My future was far from clear. In the 1940s, there were only 3 career paths for girls: secretarial work, school teaching, and nursing. Teaching was the most attractive to me, and this eventually led me to Hunter College." So while at Hunter, she gets taught a course in modern physics by a faculty member, a young faculty member named Rosalind Yallow. This is modern physics, so this is quantum mechanics. And so, Millie, I hope I'm not stealing any of your thunder, but she writes, "I loved math, but was largely self-taught in it. In grade school, our math textbooks for the semester were handed out on the first day of class. By the first week, I had gone all the way through the math book. And in high school, I took one physics course, but it didn't like much until Rosalind Yallow showed me the light. Rosalind introduced me to research and told me I was likely to have a talent for it." So Rosalind told Millie, "Shoot higher." And Millie did. Now, at the time, Rosalind was actually working part-time at the Bronx Veterans Administrative Hospital. If you go and look up Rosalind Yallow's biography, which you can because she got a Nobel Prize, not in physics, in medicine, physiology and medicine, but for radioactivity, using a radioactive isotope attached onto an antibody that would attach and recognize a protein. While at the Bronx VA, she met a longtime collaborator and friend, Saul Bernstein, and those 2 of them did this work together. Saul, unfortunately, died before the Nobel Prize was awarded, but she said, "Look, this was both our work." So it's very, very touching. Now, Rosalind, this is going to be a story about the interweaving of lives. Rosalind got her PhD from her advisor was Maurice Goldhaber, who was a nuclear and high-energy physicist, who later became director of Brookhaven National Laboratory. And she writes, "The first summer of my graduate days at Maurice Goldhaber has a brother called Gerson Goldhaber. Gerson Goldhaber was a faculty member at Berkeley. The first summer I was a graduate student at Berkeley, I was thinking of going to high-energy physics because my undergraduate was a mathematical theorist type. But I maybe wanted to do experiments, so I took a reading course from Gerson, but finally decided not to work with Gerson, but to work for my eventual advisor, Gene Cummins. But let me tell you about Rosalind talks about her early experiences. She says, Eve Curie, this is where, again, the mentoring influence plays a role. Eve Curie had just published the biography of her mother, Madame Curie, which should be a must on the reading list of every young aspiring female scientist. As a junior in college, I was hanging from the rafters. This is Rosalind Yallow, a physicist, in room 301 of Pupin Laboratories. This is a lecture hall at Columbia. She was at City College, where Enrico Fermi gave a colloquium in January of 1939 on the newly discovered nuclear fission. So Rosalind has got this connection, gets really excited. And anyway, so go back to Millie. Millie graduates from Hunter College, begins to get recognized. Soon thereafter, goes to Cambridge University on a Fulbright fellowship. And she spent a year at Bell Labs before going to the University of Chicago. Now, I have a quote, Millie. Are you going to read it, or do you want me to read it? This is, I compare notes with other people who got their PhDs. Are you going to talk about that? No? Good. As I compare this is Millie talking. and I noticed with other people who got their PhDs at the same time, this is the University of Chicago, I think we have had about as broad an education as anybody could get in any university in the whole world. Part of this was due to one individual whose philosophy about teaching physics and training graduate students was all pervasive, and that was Enrico Fermi. His idea that graduate students should learn the fundamentals of all subfields of physics, so when they decide somewhere during their graduate studies to pursue one type or another of physics, they would be able to do that. And so Millie went from field to field to field. While at Chicago, she did superconductivity. She ended up getting very soon thereafter interested in magneto-optics, using the newly discovered lasers, and works on, well, there's a lot of magneto-optics on semiconductors, so she has to be different and independent and strong-willed, which she was, and she said, well, I'll do it on, guess what material, ironically? Graphite. Okay, which sets in motion her amazing research in graphite. So she went and worked at Lincoln Labs for 4 or 5, 6 years, and joined MIT in 1967. Here's Millie as a young professor in the late 60s. And to this day, she and her husband, Gene, still have an active research group at MIT. And I was cruising your website last night. It was fascinating. And she loves these cherry blossoms, among other things. So anyway, so Millie was dubbed the Queen of Carbon Science for her work in carbon science and nanostructures. She has published over 1,300 peer-reviewed papers, books, book chapters, and review articles. So I don't think I've read 1,300 papers. She has had an incredible number of graduate students. I was looking for the number, maybe Millie, you can tell us later, but the last count I found that she wrote, she said in 2009, approximately 75 graduate students, of which a fifth were women, a lot were African Americans. And so in this web of how important it was to mentor people, Millie was certainly doing that. She was also the president of the American Physical Society, the president of the American Association for the Advancement of Science. She was the director of the Department of Energy's Office of Science, and like Eve Curie, she is a talented musician, and there she is in 1970 in an ad hoc string quartet with some physics graduate students. So that's Millie. Bert, you're next. He was also a leader. He we'll pick it up again when he went to college. He went to college at MIT in 1948. It happened to be the year I was born. So, he wasn't as young as Fermi. I looked that up too. But anyway, so as an undergraduate, he starts working in a laboratory of Francis Bitter, who had this great magnet lab. And during that summer, he actually worked on atomic physics. And not only atomic physics, he worked with a fellow by the name of Martin Deutsch on an atom that's an electron and a positron called positronium. And this is somewhat ironical because I did that too for a while. But in any case, so he stays at MIT graduate school, and his first experiment, this is great because it's connected to Fermi again. He uses the cyclotron to make a short-lived mercury isotope, but this time he's using an accelerator, and this time it really is bizarre because he was turning gold into mercury. Unclear on the concept, Bert. But he was successful. I can just say that this work was not motivated by commercial interest. So it was a successful experiment. He gets the short-lived isotope. I think you measured a quadrupole moment or some, God knows what. Anyway, it was an undergraduate. No, his first year as a graduate student. But he gets, he says, well, so he spends eventful interlude working at Brookhaven, where Maurice Goldhaber is now a staff scientist. And he decides, this accelerator is nice and the high, atomic physics and radioactive nuclei is nice, but I think I really want to do high energy physics. So he comes back to MIT and works, they have a higher energy synchrotron, and he begins to work on that. Working on QED, which I spent the first 10 years of my life working on, and testing QED, I was doing it more precisely. He was doing it at higher energy, shorter distances. When does QED break down? And so that led him to his saga. In 1957, he joined Stanford's so-called High Energy Physics Laboratory, otherwise known as HEPL, and they were making increasingly more and more powerful electron accelerators based on microwave technology that the Varian brothers had invented during the war. And they were making higher energy accelerators, and he did his first QED precision experiment there, testing that. And in that same machine, where at that time Bob Hofstadter was, this is now the Mark III. Were you on the Mark II or the Mark III in that? III. Then there's a discrepancy, because you said 700 GeV and Stanford claimed 700 MeV and Stanford claims 1 GeV. Were they overselling?
No, it was the group.
Ah, they get better. Oh, got some details. Okay, so as I try to figure this out, and that's why it was taking so long. So anyway, Bob Hofstadter took these electrons and he did inelastic scattering off of nuclei. And with that, he, in light nuclei, he can actually, if you will, determine the form factor, effectively the radius or size of the proton, and gets a Nobel Prize. Now, in that same year, 1957, Ed Ginston, who with Marvin Charrow built Mark II, were thinking bigger and bigger accelerators. They were joined by Bob Hofstadter, who was getting his Nobel Prize work, P. Smanowski, who was hired by another gentleman in the physics department named Felix Bloch. He was actually poached from Berkeley. They had a gentleman's agreement they would never poach anybody, but he broke it. And Leonard Schiff. So the team of them went to the president of Stanford University, Wally Sterling at the time, and said, can you support us because we want to build a really big machine. And we need your support, and we're going to go to the government to get this. And so talks went on, and then the DOE called the Atomic Energy Commission proceeded. But then there began to emerge a disagreement. So Hofstadter, Pief, Leonard, Ginston, they all wanted to build this big machine. But in the end, Felix Bloch said, well, wait a minute. We want to still have control over the machine. What does control mean? You get to decide who has beam time and who doesn't. And the DOE and the other guys said, well, if you're really going to get big piles of federal money, you might have to surrender a little control, like the scheduling committee, to a not Stanford committee. Seemed reasonable. Bloch, by the way, these are not lightweights. Bloch got a Nobel Prize for NMR. Hofstadter got a Nobel Prize. And so then, Bloch recruited Pief to run HEPL. And then there started to be this disagreement between Pief and also Sid Drell, who was another faculty member at the time. And so this machine that was dubbed the Monster, because it was going to be effectively 2 miles long, and it turned into a bitter dispute. And there was a breakup. Pief and Sid went and founded SLAC, officially dedicated in 1962, and Bloch and Hofstadter stayed in the physics department, and it was bitter. And I'll leave it at that for the moment. So now SLAC, meanwhile, goes on and becomes extraordinarily successful. They're just breakthrough one after the other happening. And again, by a judge of it, there was the Parton model and Feynman stuff and everything, the quarks, and there was, but there were also 3 Nobel Prizes. The first one was Burt Richter, who discovered a particle called the psi particle. And this is a picture of Burt in 1974, the year they discovered it. Marty Pearl is on the left, and Gerson Goldhaber, the guy I was taking the reading course from at Berkeley my first year, was on the right. In the background, you see on the monitor this particle track that looks like an upside-down psi particle, okay? Now, the plot thickens because another competitor was independently discovering the same particle, but by a different name called J. There was a big flip-flop of that. It turns out that Marty Perot that's Sam Ting. Marty Perot was Sam Ting's advisor, thesis advisor, so it's very interwoven. And they decided eventually to call it the so-called J-psi particle. I don't know whether there was a big debate on who came first or not, or what sounded better, but that's what happened. Now, SLAC, meanwhile, is going great guns. That was the first big victory. There are many other big victories. Again, in 1990, I mentioned very briefly, the quarks, and Jerry Friedman, Henry Kendall, and Dick Taylor at SLAC, were awarded their Nobel Prize, and then Marty's Nobel Prize in 1995. Now, you can imagine what happened, because all these Nobel Prizes were rolling out of SLAC. Physics hadn't had one for quite a while. Our shell was the last. And they were quite proud that SLAC was doing better than physics. Then I got a Nobel Prize in 1997, and Bert smiles and comes up to me and says, okay, now it's tied, 3 apiece. You finally caught up. And so I said, oh, how about Mel Schwartz? How do we count Mel Schwartz? Well, Mel Schwartz had been a faculty member for about 20+ years, had left the physics department a few years before he got his Nobel Prize, so we decided it was a pass. And now we're going to have to figure out how we count the prize for the crystallography. I guess you guys would want to count this. And there was another one. But he wasn't on the SLAC faculty. Whew. Who says physicists aren't competitive? Anyway, I have to say, when I did get to, I had heard all these stories, some of them from Sid, but when I did get to Stanford, things had calmed down. On both sides, Peef and Sid were very gracious. Felix was no longer there, and Bob was very gracious, and then the younger generation was forgetting this. So, all right, so let me just show you. So in 1998, Stanford Physics Department decides to get some of their Nobel Prize winners together. So the one really not shown is Mel. So this is pretty good, from left to right. There's me, there's Marty, there's Art Schell, the inventor of the laser, Bob Laughlin in the back. There's Burt Richter, there's Dick Taylor, and there's Doug Osheroff. So this was a pretty good run. So over a 10-year period, Stanford got 6 different prizes. Not bad, except if you're a member of the faculty at Stanford and didn't have a prize, it was bad. It was like Eve, Curie. But anyway, let's see. Oh, I took the last one out, good. So SLAC, it was a more distinguished picture of Bert. But anyway, Bert was the director of SLAC from '84 to '99. He was at that time also the president of the American Physical Society. I don't know how you do that, but in any case. And then when he stepped down from the lab director, he started doing a lot of other things. He got very interested in energy, environmental issues, sustainability, energy efficiency. He co-chaired an American Physical Society report on energy efficiency. He wrote a book, Beyond Smoke and Mirrors, Climate, Energy in the 21st Century, that got the 2011 Phi Beta Kappa Science Book of the Year prize, and on and on and on. Right now, he, among other things, is helping us in the Secretary's Energy Advisory Board subcommittee to look at small modular reactors. Now, I'm going to finish my little degrees of separation because it comes back to everybody. So Bert, in 1990-91, I became chair of physics. Bert was director of SLAC. There was a fellow by the name of Matt Beasley who was an applied physics chair. And the 3 of us decided to get together, I think we met quarterly, to start talking, because these 3 sections of Stanford physics weren't even talking to one another, literally. And so I said, well, come on, this is silly. This is like 25, 30 years after the fact. And so all of us started talking. Applied physics, I was actually, when I was hired, I was the first joint appointment in physics and applied physics, but if you look at the roster now, it's 1/3 joint appointments. Then there was a second term that I had, 2000-2002, and there's the irony. In that time, the grandson of Maurice Goldhaber, the grandnephew of Gerson Goldhaber, a fellow by the name of David Gerson Goldhaber, became an assistant professor in physics and applied physics at Stanford. Amazing. The other amazing thing that happened during that time is that SLAC and physics made their first joint appointments in faculty, which turned out to be Christmas night negotiations on some of this stuff. But it was very, very exciting that Roger Bamford, Steve Kahn, were very, very exciting. And so now there's a good working relationship with SLAC, with applied physics. One more connection. Sid Drell had a son and a daughter, well, a couple kids, 3. And Persis is the daughter of Sid Drell, now director of SLAC. When she was a first-year graduate student at Berkeley, she decided to work for Gene Cummins. I was the final year of my postdoc, and I was assigned to, I guess I was teaching her how to machine, not to saw a graphite box. I claim she denies vigorously that I taught her how to drive stick shift and drink bourbon. No, actually, the bourbon part, father claims that he taught her how to drink. That's it. And then when I went to Bell Laboratories, I actually became her official graduate research program for women. It's a program, and I was her mentor. She came to Bell for a couple weeks, maybe a month, and worked. So it is a very small world of this interweaving of everybody. So it may look like a big world, but it is very small. So anyway, Millie and Bert, and also to LaRose and Jean, in recognition of your long record of outstanding scientific contributions, your public service, your mentoring, I want to say how happy I am personally that you have been awarded this, and please accept the President's, the country's, and the Department of Energy's warmest congratulations. Thank you. Okay. Anyway, that wasn't too much over, was it?
Half hour. All right. Now Steve's going to hand out the citation. We'll give Millie your award first. So if you step over with Steve, he will give you the medal. And the citation here for Millie is for leadership in condensed matter physics, in energy and scientific policy, in service to the scientific community, and in mentoring women in the sciences. Millie? Okay, now for the award for Burt Richter. The citation for Burt is for pioneering the development and application of positron-electron colliders, visionary leadership as director of the Stanford Linear Accelerator Center, and important contributions in science and energy policy nationally and internationally. Burt?
floor is yours.
Well, this was a really eventful presentation. We're here in part to celebrate Enrico Fermi. This is the Enrico Fermi Awards. And I was going to make a few remarks about him because I'm probably one of the very few people in this room that knew him and studied with him. So I thought you might be interested in some personal anecdotes about him. We didn't hear so many of those, did we, Steve? I think you've done everything else, Steve. But, and there was one thing that you left out about me that I wanted to mention that I think is kind of important. And this is my $5 education. Okay, so I have to tell you about that. Because, in growing up in New York, I think that I grew up in New York, and so did Bert. And not so far from each other. There were some overlaps there, maybe, because Steve was telling about overlaps, so I think we had some overlaps, perhaps. But we didn't know each other. So my education was at Hunter College, and I wanted to say a few good things about Hunter College. Yes, Rosalind Yellow was there, and she introduced me to physics, and that was good, right? But what I learned about that place was enough physics to get into the University of Chicago. Nothing too much, but enough. Sometimes enough is enough. And a second thing that I learned was that a free education is not exactly free, because when you don't pay, there's somebody else that's paying for you, and that's society. And I wanted to say that the availability of affordable higher education beyond high school, which is public for everybody, I think should be a goal of this country, because we learned from World War II when the GIs came back, and they had an affordable education too, very similar to what I got at Hunter College. And they made a tremendous contribution to the future of our country. So we should kind of think this one over. Right now, we're getting further and further away from affordability of college education. And maybe the concept of getting people that get this so-called nearly free education to pay back wouldn't be a bad model for us to think about for policy of the future. So, okay, that's a little bit of preaching that I didn't find in your talk, so I added that. But now going on to a few other comments, there really isn't a whole lot for me to say more, but I did know Enrico Fermi, and I wanted to have a few anecdotes, tell you a little bit about him. So I wound up to be a graduate school student at the University of Chicago in 1953. And you remember he lived one more year. So we had 1 year of overlap. 1954, he passed away. But all of 1953, he was in very good health, as far as we knew, and he was very active. And that was the time I knew him. We heard that he was a great scientist and human being, and we heard a little bit about teacher, but we didn't hear much about that. And that's what I was going to tell you something about, because he did influence a whole generation of scientists in the U.S. Before he came to the U.S., he was, in his early days, in Rome. And at the age of 26, he became the head of the physics department there. And he was the one that educated the Rome school, and that was a very powerful school in nuclear physics at that time. and everything else. They really knew everything. They were very broadly educated. So Enrico Fermi was a fellow who spoke very, very slowly. And he spoke very clearly and succinctly. There was no extra wordage in what he had to say. He just said it, and that was it. He would often tackle very complex problems, and I think we heard that from Steve. But he liked to have answers to problems that were very simple. And he liked to be able to write the solution of any problem that came upon him on the back of an envelope. And in his lapel, he always had a couple of envelopes of what he had done that day and the day before. That was his trademark. So you have heard about back of the envelope calculations. I think many of you heard that. That's where that phrase comes from. Okay, I told you about that. Yes, the next topic I wanted to tell you, I took a course of quantum mechanics from him. I think we heard that from Steve, or maybe we heard that from Bill. We heard from somebody about his quantum mechanics course, and he had a thermodynamics course and a few other things. I was in his quantum mechanics class, and everything was very simple, very simple. And you thought it was simple until you got home. And the class, every class, without exception, ended with a problem. And the problem, also, the lecture sounded simple, and the problem sounded simple. But the problem was due the next lecture. So we had Monday, Wednesday, Friday. So we had a day to do this, and it was a lot of work to get from A to B, because the first thing was to understand what the problem was about. That was and I think we learned a great deal from him in the formulation of problems of physics, how to think about physics, how to solve problems, and how to generate your own problems. So that was what we learned. We learned from him that it wasn't enough to learn what he was teaching, but his idea that we should learn all of the different kinds of physics that were taught in the department, and we were examined on them. The exams were quite exhaustive or intensive that we got at Chicago. I think they were well known. But the objective was not to punish us, but it was to teach us that if you wanted to do anything in this field, it was a good idea to have a broad knowledge. And I'm very thankful for that, because the broad knowledge has helped me in my career, especially when I had to move into other areas that I didn't know very much about. I at least had some fundamental background going back to my University of Chicago days. So we had class notes. We heard about the class notes from Steve. The class notes were generated in a way that he didn't explain. During class, we were more or less forbidden to take notes. That was not what was expected. But at the beginning of every class, he gave us the notes of what he was going to talk about. And he prepared them just before class. Yes, that was the system. He came in early. He liked to get up early. And when he had to give a lecture, he would prepare his handwritten notes, give them to us. And it wasn't quite like the lecture, but it was sort of like the lecture. And that helped us. And we heard about all the mistakes. I think that was part of the intention, because when you worked the problem and you used maybe a mistake, it didn't work. So you discovered yourself that when you read the physical review or whatever literature, they're not always right, okay? We learned that as students. Important thing to learn. I meant to also say that my laboratory where I did my thesis was under Stagg Field. So I was right there before they tore it down. It was quite radioactive when I was there. But I'm still here. So we can figure out that some people are more susceptible to radiation than others. Another thing I wanted to tell you is that Enrico Fermi lived quite close to the laboratory, and he walked to school every day. And he knew every student in his class. The classes were very small, but he knew each of us. And when he would see us walking, he would cross the street and walk with us and chat with us. That was his way of being friendly. And I was an early bird, he was an early bird, so I used to see him pretty frequently. And I had these walks with him, which I really cherish, and I remember them for all these years. Another thing that Enrico Fermi did is we had dinner at his house about once a month. I remember those dinners. Laura Fermi was a very, very good Italian cook, and it wasn't only the cooking, but it was the ambiance and the friendliness in that household that really made us enjoy physics. That was something more. Very, very few people do that. You get into the sort of family thing. That's something that we didn't hear from Steve, because maybe he didn't know about that, but maybe now he's happy to hear about that. We heard about that Enrico Fermi was at the forefront of every field of science. In fact, he even got into computational science at the very end of his life. So he really covered all the areas. We heard about his service to society. This was a very, very important part of his life. And this was something that he taught us. He said that this was an important thing to do. In the 1950s, there were many, many scientists that were working for the government. And I think that John Holdren, you would enjoy having helpers, and Bill. And that's the way it was in the 1950s. It wasn't that I was involved, but my professors at the University of Chicago were always traveling back and forth in service to the country. Okay. I wanted to say that teachers like Enrico Fermi are really important to have around because they influence people and they change your whole life. So I feel that Enrico Fermi has done that for me. But he's not only done that for me, but he's done that for many other people, everybody whom he touched in his interactions. So I say a few things about the legacy. So we remember him for all the science. We heard from Steve many of the things he did. It's a very, very long list. We remember that. We remember him as a teacher. I was talking about that. But I think the teaching methods that he taught, the way you teach physics to students, was very important in the 50s and 60s. And I think it had a big influence on how we dealt with Sputnik when it came, because there were many people around the country trained to be able to take off and move with many students to amplify the impact of physics to a much, much larger community. And I think that is part of his legacy. Without him, and maybe a few other people like him, things would not have moved as quickly as it had as physics expanded, science expanded in that period. So those are my remarks, and thank you for listening to me.
I think I'll discard a large fraction of the 15 pages of notes I've got here. I never worked with Enrico Fermi. I never met Enrico Fermi. I never knew him, but he had a very profound influence on me. And he has always been one of my idols as a physicist. And the reason was because he did both experiment and theory. I came to feel that if you didn't understand theory, if you couldn't at least read parts of the papers and understand where they're going, then you as an experimenter are no more than a technician for the theory community. So I have always pushed all my students and all the postdocs and all the young people to make sure that they understood theory and to make sure that they could not read the papers. And unfortunately, over time, it has become more and more difficult for experimenters to do their own theory. When I was going through graduate school, I didn't know whether I wanted to end up being an experimenter or a theorist, and I did both. I got the alchemy successful, even though it was in the wrong direction. And I actually did some serious theory calculations on various reactions at the cyclotron. And so I've always pushed that. During my early days in, at the high energy physics lab, I actually did the calculations about how I could test quantum electrodynamics. I had a little bit of help from Sid Drell and some of the other graduate students, but I could actually do it myself. I think it's regrettable that our theory has gotten so mathematically complicated that I don't think that's possible anymore for an experimenter to really do his or her own calculations. The best you can do is to understand what they're doing and understand when they're talking sense and when they're talking nonsense. And there's an awful lot of nonsense out there in the theory community, and I have not been afraid to say something about it. I want to talk a little bit about my mentors, because I think to all of us who've grown up in science and who have risen to relatively high ranks in science, you've got a list of mentors who have helped you on the way. And I want to mention a few. The first, Francis Bitter, Steve already mentioned. I started working with Francis Bitter in his laboratory in the summer between my sophomore and junior year, and I kept on working with him right through undergraduate school and right on in to graduate school. He was terrific. He was very patient. He would really help a young whippersnapper out. With the positronium experiment, I have to say, Steve, I was more a gopher than a collaborator with Deutsch, but that was a very interesting system too. Martin Deutsch was mean to his graduate students and very nice to me. The reason was, since I was a mere junior, I wasn't expected to know what he expected to his graduate students to know. So he would actually spend considerable amount of time explaining things to me. If one of his graduate students asked the same question I did, he'd bite their heads off. I thought that was very interesting. Francis Friedman was a theorist I worked with. Fred Friedman died relatively young, but he was very important. He's the guy that set some practice problems for me. And working with Friedman, I did all of those problems. I could do all the calculations. I came to the conclusion that I enjoyed the plumbing of experiment a lot more than the plumbing of theory. Plumbing of experiment means I could build devices that did things and measured things. And the plumbing of theory is to solve the mathematical equations after you set them up. And while I could do that, I didn't find that part of it rather exciting. Dave Frisch was the person who helped me make the transition from atomic, molecular, and optical. And by the way, we were doing the hyperfine structure of all the isotopes of mercury, and with that you found out about the distribution of neutrons in the nucleus and so forth. But Dave helped me make the transition by fixing up this time at Brookhaven. Lou Osborne was my thesis advisor, very helpful. And Pete Panofsky taught me a lot, and in particular about how to run a laboratory. There are a lot of other people I've worked with. Some of you are here today. Some of you were critics. Some of you told me things I really needed to know, even if I didn't want to know them. And some of you are very good collaborators, and I've enjoyed it all. I also want to give credit to parts of the government. I was one of the first National Science Foundation graduate fellows. That meant a lot to me because the money was mine. And so when I decided that atomic, molecular, and optical was not for me, I didn't have to go find a mentor or another person who would put up the money to support me. I had it from a National Science Foundation. And with that, I could move off to Brookhaven for a while. I could come back and start working on the MIT synchrotron. It's terrific. And I take one of my accomplishments at Stanford is to help convince one of our presidents that he should set up the system of fellowships, the presidential fellowships at Stanford, which give graduate students the money themselves, so they don't have to worry about that sort of thing. Anyway, I ended up as experimenter, and I ended up as experimenter who understood theory, who back then could do his own calculations. I couldn't do the calculations now. And I look back and say, physics has undergone another division. I think I may be the last, or nearly the last, of the experimenters who built their own accelerators to do their own experiments. Way back, there were natural philosophers before there were disciplines, and then we went to disciplines with chemistry and physics and geology and what have you. The split between experimenters and theorists didn't really become serious till the 1920s when quantum mechanics got complicated. But the accelerator builders and the accelerator users were the same people until the 1970s when the accelerators started to grow so expensive that you couldn't turn them over to somebody who hadn't been through the mills. And so I don't see people now who both design and build accelerators and design them for a particular reason and use them to do that sort of physics. It's getting late, and I want to short circuit all of this. All I want to say about why it's the J-Psi is when these two papers got published in the same issue of PhysRev Letters, Sam Ting's paper hit the office 12 hours before ours did. And so in the journal, it's first Ting's paper, and then it's the Stanford paper. And so Ting was the J, and we were the Psi. I've always insisted on the West Coast that it be the Psi J, but that's not universal anymore. We shared the Nobel Prize in 1976, and that faced me with a problem. Problem was, here I was 45 years old. I'd already climbed the highest mountain in science. Did I want to keep climbing that mountain? Did I want to do something else? And I decided I wanted to do something else. I wanted to not run big physics groups anymore. I wanted to run a laboratory and do things to get more science done than I could end up doing all by myself. And so I became Panofsky's successor running SLAC in 1984. I learned a few things as a lab director, and the first thing that you learn is you cannot remain on the frontier of science if you're going to continue to do the same thing all the time. Science moves on, and things change, and you've got to change with it. And so in the 60s and 70s, SLAC was, I think, although its energy was a long way from the highest, it was the premier lab in high-energy physics. Today, I think we're the premier lab in what's called photon science. We have the world's first X-ray laser. The demand for time on it is terrific. And we still have a high-energy physics program. We have a particle astrophysics program. We're on satellites flying around. The biggest program at our place now is the photon science. When I started at SLAC, when SLAC actually turned on, it was open to the science community. We had 100 users. We have 3,000 now who come in to use the facility. So it's people voting with their feet say, we were a success. We remained a success over the years. We are a success. If that 3,000 starts to go down, the next director has got to do something. I can't resist saying something about Persis and why I started paying attention to Persis, because it comes back to Fermi. She got her degree and she started doing high energy physics. She started working at SLAC. And the first paper that snapped me to attention was, in fact, the analysis of the radiative corrections on Z boson production that she did with a couple of others. And this was a serious piece of theory, and I said to myself, aha, somebody who does theory and experiments has got to go far. Anyhow, so lessons learned as a lab director: you can't remain on the frontier by doing the same thing. The easiest way to get something done is to convince other senior people in the lab that it was their idea in the first place. If things go well at your laboratory, you get the credit no matter who thought it up. It's always good to tell the DOE what you have done after you have done it. But sometimes it is a very bad idea to tell them before you've done it. And in Washington, there's an exception to every rule, and no means maybe. So if I want to criticize my friends at DOE, I would say there's one problem that they really ought to go work on, and that's what some have called atomization. When I was lab director, we had a handful of what are called B&R codes, budget and reporting codes. Those are the pieces that are sliced and reviewed. I looked at our 2010 budget. We had 165 of them for physics. You have these laboratories, so let them do large-scale things, and the laboratories have much broader talent bases than you can possibly have in Washington. So the theory in perfect form, if it worked this way, it would be wonderful. The labs could tell the DOE what could be done, and then the DOE chooses what will be done, and they should choose it in big pieces and give people a lot of credit. Some nice things about the DOE: I completely agree with Bill Brinkman. The Energy Frontier Research Centers at the Office of Science are terrific. Basic research can be done in targeted areas. If you want to understand the fundamentals of catalysis, that's great basic research. It also will help you make better fuel cells and do all sorts of other things in the energy business. The Energy Innovation Hubs are an attempt to bring together industry, university, and the labs to accomplish big things. That's terrific. And ARPA-E is aimed at programs too risky for industry, and I think it's doing a terrific job. So let me say that DOE and its programs are important to the nation. It's the biggest supporter of research in the physical sciences. In the energy area, it's the main player in areas where industry no longer treads. And when you get battered by committee members, remember that it's an election year and off years are always better. Thank you all.
Okay, and now for the next slide. Now, you've been very patient. I hope you can all join us at the reception, and I think we will draw this conclusion, but let me again say how wonderful it is for us to have these two wonderful, wonderful scientists, public servants, mentors as the Fermi Award winners, and again, very much congratulations from our country.